going to go back and revisit something that we addressed early last week. That's called free body diagrams. A free body diagram, you might remember, is a diagram that shows all of the forces acting on a particular object. Now, we drew a couple free body diagrams last week, but that's kind of where we ended it. We didn't do anything with those free body diagrams. Today, we're going to see the purpose of drawing those free body diagrams. The reason we will draw diagrams that show all of the forces acting on an object is so that we can analyze more complicated force problems. Up until now, we've analyzed problems involving one force or another. Maybe it's been friction. Maybe it's been an applied force. Maybe it's been some other force like wind resistance or air resistance. But it's been one force. Today we're going to learn how to analyze problems involving friction and air resistance, or gravity and a normal force, not both. Or sorry, not one or the other. We're going to analyze problems involving more than one force. But to do that, we have to be pretty comfortable with free body diagrams. So we're going to go back and revisit free body diagrams for just a few minutes, and then see where we're at with that, and then go on to those multi-force problems here. The best way to do that is to do an example. 3.1 on page 131. Have a look. It says a car with a weight, which of course we know what weight means, right? That's force of gravity, as opposed to mass, which is the amount of matter that's possessed by something. A car with a weight or a force of gravity of 10,000 newtons down is coasting on a level road. The car experiences a normal force of 10,000 newtons upward, a force of air resistance of 2,500 newtons backwards, and a force of friction also exerted backwards. We want to draw that free body diagram. So here's my road. Here's the car. Let's try to draw this car so that it actually kind of looks somewhat like a car. A little bit. There we go. There's my car. We got a headlights on the car. We've got brake lights back here. And, oh my goodness, wouldn't be a fast car if it didn't have lightning bolts on the car. So there's your really fast four-door sedan that has a weight of 10,000 newtons acting down. We're going to draw that downwards here. FG, 10,000 newtons. Now, we could also draw a normal force acting up. It should be the same length. Now, I'm not going to measure it when you draw yours to see if it's the same length. If it's approximately the same length, then that's fine. It doesn't have to be perfect. Just understand that vectors, when we draw these vectors on these free body diagrams, it's just like when we're drawing vector diagrams with displacement and velocity. We should draw them more or less to scale. Now, I could have drawn that normal force down here as well. I chose to draw it up there. It doesn't matter. As long as you draw it at the right length and in the right direction, it doesn't really matter where you draw it. So that's as good as anywhere. Now we've got a force that's exerted to the left of 2,500 newtons. That's the force of air resistance. I'm going to draw that about this long because the force of air resistance is only 1/4 of the length of the normal force and the force of gravity. Now, is that exactly 1/4? I don't know. I didn't measure it, but it's close enough. Clearly, you can see from the diagram that that's a smaller force than the normal force or gravity. Now, we have one more force here as well. It's 500 newtons backwards. You got a choice here. You can draw it 500 newtons backwards right there, but that looks a little bit cluttered sometimes. So maybe we want to draw the 500 newtons backwards right here. It doesn't really matter where I draw it. As long as it's pointing in the right direction, which it is, pointing to the left here, and as long as it's drawn more or less to the right length. And it's not perfect here. It's probably not 1/5 of the air resistance force, but it's close enough that it'll work for us. Let's have a look at these two questions, okay? See what you can do with those for the next, we'll give you about 4 or 5 minutes, and then we'll take a look at them as a class, and then we'll actually put our feet into the real purpose of today's lesson, and that is to solve those multi-force problems. All right, let's Let's take a look at 1 and 2 here. It says, number 1 says, the driver in example 3.1 sees a pedestrian and steps on the brakes. The force of air resistance is 2,500 newtons backwards, and there's a force of friction of 5,000 newtons backwards. So here's my car. I still got a force of 10,000 newtons acting down. Okay, that's the force of gravity. I've also got a force of 10,000 newtons acting up. That's the normal force. Notice this time I drew the normal force underneath the car. Last time I drew it above the car. It doesn't matter. As long as it's drawn the same length as gravity and as long as it's drawn in the right direction, any position is fine. Now we have air resistance acting backwards. So we're going to make that 2,500 newtons. And we're going to make it about 1/4 the length of my normal force vector. Now I'm also going to draw my force of 5,000 newtons acting backwards. That should be about half the length of my normal force, and that's going to be my force of friction. We could have, if we wanted to, draw that 5,000 Newton force of friction over here. It wouldn't really matter. Okay, I could have drawn it over there to look a little less cluttered, but in the end, it shows me all of the same things, no matter where I draw it. 2, car moving at a constant velocity starts to speed up. The weight of the car is 12,000 newtons. So here's my car again. There we go. Little two-seater this time. My car has a weight of 12,000 newtons down. Now, notice here that I've drawn my force of gravity smaller than I have drawn in the last case. That doesn't matter. You don't have to draw it to the same scale as your last question. You just have to draw it to the same scale, Zach, within this question. Now, we've got a normal force acting up, also at 12,000 newtons. And this time we've got an air resistance acting backwards, 3,600 newtons. Let's draw that this way right here. And we've got a force of friction that actually propels the car forward because it's friction between the tires and the road as the tire is turning. So it's going to be a force that it acts opposite to the way that air resistance acts. It's 7,200 newtons. It should be about like this, longer than the 3,600 newtons, shorter than the 12,000 newtons. We'll call that FF, the force of friction of 7,200 newtons. And that's it. That's it. Does that make sense? All right, so now it comes time to see exactly what we're going to do with this, the whole purpose of drawing these free body diagrams. Again, up until now, we've solved problems involving one force or the other, but not one force and the other. Today, we got to learn how to do both. So here's the steps we're going to use to solve problems involving more than one force. First thing is draw a free body diagram. Okay, that makes sense considering that's what we've just focused on, and that's why we just did it. It was so that we could solve these multi-force problems. Get your free body diagram. Now, this last sentence says, cancel out any forces that you can. Cancel out any forces that you can. What do we mean by that? Let's go back to the problem that I just did. That's problem number 2 on our practice problems. There's 2 forces in this practice problem that I could cancel out. Which 2 are they? Michael? Good. Why could I cancel out gravity and normal force? Yep. Good. They're the same but opposite direction. So you got a force of 12,000 up, force of 12,000 newton down. It doesn't really matter because they cancel each other out. So cancel out any forces that you can. In that last problem, there's nothing else I can cancel. If I had a force of 3,600 to the left, 7,200 to the right, and then another 3,600 to the left, then the 3,600 could cancel. But I don't have that. Now, if all the forces that are left over are on one plane, X or Y, but not both, then do the following. If they're on more than one plane, you've got an X and a Y, well then we're going to tell you about that in about a week. Okay, for now, they're all going to be on X or Y. Do the following. step number one, write down F net is equal to F1 plus F2, or whatever forces that is that we have in our free body diagram. F net is equal to the sum of all of the forces that are acting. In this case, the example that we just did, practice problem number 2 on page 131, we would say F net is equal to F air plus FF. If we were accounting for normal force and gravity, we would say F net is equal to Fn plus Fg. But since they cancel, we didn't have to worry about that. F net is equal to all of the forces added together. Call them F1, F2 if you want. Call them FF. Call them F air if you want. Call them FX. Call them FY if you want. I don't care what you call them. Add up all the forces. If there's 2 of them, great. If there's 14 of them, that's a little bit more work, but it's not any harder. Now, the net force, sometimes we just call it F, is also equal to something else. And this is not new. This goes back to Newton's second law, what you did last Monday, a week ago today. F is also equal to m times a. So what we will sometimes do is replace F net with m times a. If F net is the sum of the forces, then ma will also be the sum of the forces. Now, you're only going to do step 2 if you're looking for the acceleration or you have the acceleration. If it's a problem that says what's the net force, then skip step 2. Just leave off the m times a and leave the first term as F net. What's the next step? Great news. Nothing else really to remember. Plug in your numbers and solve for whatever you're looking for. Just make sure you put in the numbers in the right direction, the right signs, positive or negative, and your free body diagram is going to help you with that. Right? Let's take a look at an example. 2 people, A and B, are dragging a canoe out of a lake onto a beach using light ropes. Now, the reason they're telling me that they're light ropes here is so that we know that the ropes themselves aren't going to be a part of this problem. If they were heavy ropes, then it would add to the mass of the canoe, right? And then they'd be a factor in the problem as well. The people are important because they're applying the force. The canoe is important because it's being pulled. The ropes, they don't weigh anything, so they don't really matter here. Each person applies a force of 60 newtons to the right, and there's a force of friction of 85 newtons backwards. So we're going to say FA is 60 newtons, FB is 60 newtons, and we're going to draw a force of friction back this way that's a little bit longer than the 60 newtons because it's 85 newtons. We're going to call that FF. Now, there is gravity acting on this canoe, and there is a normal force acting on this canoe, but because we're looking at this canoe from above in this diagram, it's pretty hard to draw in gravity, right? Gravity acting down and normal force acting up when we're looking at it from above. The good news is they cancel anyways, so we don't really need to worry too much about them in this case. Step 1 in that method, step 1 of 2, F net is equal to the sum of the forces. In this case, it wouldn't be F1 plus F2, it would be FF plus FA plus FB. Now the next step was to say F net is equal to m times a, but we don't need to do that here because we're looking for the net force. Since we're just looking for F net, let's just stub in our numbers here. FF is going to be 85 newtons, FA is going to be 60 newtons, and FB is going to be 60 newtons. Is there anything wrong with what I've just done? Zach? Good. Which one should be negative? Good. The 85 newtons should be negative because it's drawn to the left. Right? That's part of why I drew my free body diagram in the first place, was to remind myself that when I added them up, I had to pay attention to what was negative and what was positive. 85 plus 60 is going to give me 35.0 newtons. 3 significant digits. Okay, 1, 2, 3, 1, 2, 3, 1, 2, 3, 3 significant digits, 35 newtons. Now, if I was looking for acceleration, I'd set that equal to m times a and solve for a. But I'm not. So I skip that step 2. Now think about what we just did here. Okay, it may seem a little bit tricky, it may not, depending upon how your mind works, depending on how awake you guys are right now. But in the end, what have we just done? We've added. What have we had to do today? We've had to add. If that's as hard as it gets, then we should be in pretty good shape, right? Now, you do have to pay attention to whether you're adding or subtracting or positives or negatives, but really, it's pretty straightforward, right? Get the direction. F net is the sum of the forces. Add them up. And maybe in a really complicated one, set it equal to m times a. All right, here's your questions to work on with that. Page 132, questions 1 and 2. So your homework tonight is page 132. In addition, I want you to do page 190. That's not 190. That's more like 119. I want you to do 190. Number 1 to 6 and 10, please.